I would love if someone tells me 10 years ago when I started using R that I will present my function in R in Budapest, where my children will study in English and they will learn in even Hungarian. That's like proof that anything is possible, really. So I was working at a faculty at the Technical University in Brno, in the Czech Republic, but we moved into Budapest, so now I'm settled here. And I would like to talk to you about the approximation of powers, because I was working on that, and the last year when we were in Poland, actually, I met Przemek, who suggested that I rewrite my ideas to R code. So that's why I started thinking about rewriting it so that everyone can use it. Here is a motivation example. One friend of mine asked me, how many trials should I observe to be sure that two operators are equally effective? So we have a probability that they are successful when answering a phone, and we want to be sure that they are equal. Well, you have to tell me what's your probability of type 1 and type 2 error. That means significance level and power. At the difference between the rates. So actually I pushed him to tell me, how do you think if they are equal, what's the probability of positive answering or success at the call, and which difference in the rates would you like to see or distinguish? That's an easy example. You have two binary variables which are independent, and you can test the null hypothesis on equality of them, of the rates, of their probabilities. So, for example, you can use a PUR package in R, which actually uses arcsine square root transformation. But actually, that makes it's a variance stabilizing transformation, and you can even make better than this. So now you would use GLM for comparing the two p-values. So this, I would say, it's not that powerful. And I compared that with my student, or he was working on that mainly, and we all really saw that it's better to use GLM than just variance stabilizing transformation before the comparison. Or you can use the function in stats package, but both of them allow just to compare two probabilities, two binary variables. Or you can use simulations. If you have another variables that are normal and you have more of them, you want to test that their expected values are equal, you can use power ANOVA tests to suggest which sample size is sufficient to distinguish between the expected values, some difference between them. So to actually be able to decide on the sample size, you need the power, so-called power function. And for that, you need to know the distribution of the test statistics used under the null hypothesis when the expected values are equal, and under the alternative you are interested in, so when they are different. And so here you have some suggestions what you can do, but what if there is more than two operators? So you have binary variables which are but more than two. And what if the observed variables are not normal and or binomial, binary? In that, here I have to assume that we have just one factor influencing the expected value. That means we can only compare several groups of samples. And I will focus on equal sample sizes. So I can't have groups of different sizes. Well, the answer is you can use GLM to test the hypothesis. GLM means that the response variables have a distribution of exponential type. I don't want you to read that. It's just that it depends on some function B, which is a function of a parameter theta, which is important here, and we will actually model it. And this one is some nuisance parameter that influences the variance. And in the GLM, we tie the parameter theta through this derivative of the function b to the linear predictor, which describes actually the expected values. So that's called the link function. And so into this group of distribution fits Poisson binary distribution, gamma distribution, normal as well with known variance, negative binomial, and other. There are also multivariate version of those, and there would fit a multinomial distribution, but I'm not presenting the results for the multivariate version. And we are interested in testing the null hypothesis that the expected values are equal. Well, this is just the table to summarize the things. So we have M groups, and in each group we observe the same number of units. We can calculate the mean, and as we want to test that the expected values are equal against that they are different. So we in GLM you use the maximum likelihood theory, and the maximum likelihood estimators are needed to test the hypothesis that the expected values are equal. For that you need to have the estimates of the parameters under the null hypothesis and under alternative, which are for the expected values are directly the averages. And because of the central limit theorem, we know directly that they are asymptotically normal. And to test, you have three possibilities. You can use maximum likelihood test, which in the notation of GLM is the deviance. You can use score test, or you can use Waltz test, which is a quadratic function of the estimates of the parameters, like those betas. But I was just working with deviance and score statistic. And in this case, you can rewrite those in this form. So if you know the distribution of those two test statistics under the assumption that the expected values are different and that they are equal, you can easily derive the power function and then decide on the sufficient sample size. Well, looking at this, you can't derive that directly. So you can use a trick that is usually frequently used in statistics, that you just do Taylor polynomial and try to find the distribution of the statistics, which is actually this form. So if you find the distribution of that statistic, you know that the original one converges in probability to this one, and both have the asymptotic distribution the same. So this is done after some calculations. You see that you have to subtract some constant, and then you get the quadratic form, which is not very easy. You have a distribution of linear combination of non-central chi-square distributed variables, which are independent. So well, we have the distribution we were searching for. Then there is a next step. If you want to evaluate the distribution function of that distribution, you cannot easily find it in R or in code. You cannot easily calculate it. You have to call a package, which I will mention at the end of the presentation. And luckily, under the null hypothesis, as expected, and usually in GLM is mentioned, the test statistic has chi-square distribution with -1 degrees of freedom. So actually, I should mention for that calculations, you need to have a no, you don't see it here. So, well, the parameters of the linear combination here are we obtain them by spectral decomposition. So actually, to calculate the approximation of the power, I have to calculate some spectral decomposition, and this matrix and the constant here, those are dependent on the type of the distribution which I considered in the GLM. And here I have a derivation of the asymptotic distribution for the score statistic, which is much easier because if we just substitute the average by its expected value, then we have a quadratic form. So this is much easier. But unfortunately, again, we have a linear combination of independent non-central chi-square distributed variables. And similarly, under the null hypothesis, I have chi-square with -1 degrees of freedom. So then I can easily derive the powers of the tests, like probability of rejecting the null hypothesis, and the alternative, which is identified here by the vector of expected values. And I need the distribution function of that silly, difficult distribution. So the similar is for scores test. And now I have an easy example. I have 4 samples actually, and with increasing expected values. So I have some baseline mu, which increases in each sample. And I will show you the approximation of the powers, which are just described for those 4 distributions. So here we have a gamma distribution. These are the different colors are for different base expected values. And then sample sizes above, I have 5 sample size in each group, and here I have 10. So if the higher the sample size, the better the approximation. So the full line is for approximation for deviance, which is simulated by the squares, or the squares is the simulated power, and the approximation for score, which doesn't work very much for the gamma distribution, but with the increasing power is much better. Here is a result for Poisson binomial as well, and negative binomial. So the implementation was a great joy for me because I made it after a day. It was working and I was just jumping around the computer. It works and it does things I didn't expect to do. I must say I was looking into the source of the PWR and the power function of ANOVA to find out how to do that and learn from it. So actually you can, in the function, you settle the expected values you assume in your samples. So this is a vector. Then you have to specify the family similarly to GLM. So you can have Gaussian like defaultly, but we have I just wrote the function for binomial, Poisson, negative binomial, and gamma. in some cases, the nuisance parameter appears. For binomial, is the number of trials. For gamma, there is one nuisance parameter, and so on. And you can specify which test you want to use, either deviance or score, or actually both. The function works the same way as those other functions I mentioned. So you have to specify two of a triple. So sample size, which is this n, significance level, and power. So if you are missing one, the function will calculate it. So if I have settled the significance level and power, the function calculates the sample size. Well, here is the package I'm using for evaluating the distribution function of linear combination of independent non-central chi-square distribution. So here I have a small example. I took those telephonists, but now I have 3 of the girls. And I have a baseline, which is mu. And here the matrix M is just consists of vectors of different each column corresponds to one of the telephonists, the expected values, and the rows correspond to different values of age. So actually I can call the function to get a power function, and then with this result I can plot both of the functions and compare them. And also I can do the power calculations. So if I specify just one example here with those probabilities, I get the result in such a case. So here I have power calculations for deviance and score test. And also I can do sample size calculations. So I specify the power and significance level, and the function calculates the sample size. So here I have a sufficient sample size of 128. And here is so this is for deviance, and for score test with 130. So actually you can choose only one of the tests. And this picture is here because I noticed, being new to this conference, that you all like hexagons. So I have many of them, and I got one feeling that we are all as bees working on our one hexagon, and then it makes an amazing beehive full of something that's valuable, and that actually filling each hexagon brings a lot of joy. So I hope that you will enjoy filling your hexagon, and hope that you will enjoy the remainder of your stay here. Thank you.
Very nice cool down of the conference. I'm looking at the audience. Does anyone have any questions to Zuzana? Because if not, then this time I wouldn't ask anything, because it turns out that in the other room they've just finished the presentations. Thank you, Zuzana.
Thank you very much. Thank you.
But Gergő told